Hey everyone, we're wrapping up section 9.5 in this video, taking a look at a couple more applications of quadratic equations. So first up, I want to go over, one of the most well-known formulas in mathematics, the Pythagorean theorem. So if A and B are lengths of the legs of a right triangle, and C is the length of the triangle's hypotenuse, then A, B, and C have the relationship that A squared plus B squared is equal to C squared. And just in case that didn't really make a whole lot of sense, here's a picture. That's a right triangle because it has a right angle. A and B being the legs means that they are the sides that are attached directly to the right angle. And the hypotenuse is always the side of the triangle which is opposite the right angle. So A squared plus B squared is equal to C squared. And what we're going to do is use this formula in our next example. All right, the sun is casting a shadow from a flagpole, and the height of that flagpole is 3 times the length of that shadow. So if we know the distance between the end of the shadow and the top of the flagpole being 20 feet, we want to find the length of the shadow and the length of the flagpole, rounding all answers to the nearest tenth. So here's a diagram. We have a flag, and the sun is shining on it. That makes a triangle. You can see right there in yellow. The flagpole is one leg of the triangle. The shadow is the other leg of the triangle. What we know is that the distance between the end of the shadow and the top of the flagpole is 20 feet. So we know that this length here is 20 feet. That's what the problem says. All right. Now we need to figure out what it is we're looking for. We're looking for the height of the flagpole and the length of the shadow. So I need to call that something. Let's let S be the length of the shadow. If the flagpole is 3 times the length of the shadow, then the length of the flagpole would be 3S. Since this is a right triangle, we can use the Pythagorean theorem, which says that if I square the lengths of the legs, in this case it would be S squared added to 3S squared, that should be equal to the length of the hypotenuse squared. So get S squared plus 9S squared equals 400. And this is not bad at all because we have 10s squared equals 400. Quickly use the square root property because we can divide by 10. We'll have s squared is equal to 40. So s is equal to plus minus the square root of 40. Now, again, it doesn't make a whole lot of sense for a length to be negative, so actually we're just interested in the positive solution. 49 is not a perfect square though, so let's simplify it maybe a little bit. So it would be 2 times square root of 10, and we're told to round to the nearest tenth, so let's do that. Get our calculator out, and that would put the length of the shadow at about 6.3 feet. So the flagpole, remember that its length is 3s, so this would be about 3 times 6.3, which is equal to 18.9 feet. So we have that the length of the flagpole is 18.9 feet, roughly, and the length of its shadow is about 6.3 feet. All right, one more. This next one's a little bit of physics. So, I suppose based on our experience, as human beings on this planet, even if you haven't taken a physics class or it's been a long time, you know that if you take an object and you throw it straight up, it falls back down due to gravity. So that's what we're going to be looking at. So here's a formula. The height in feet of an object shot upwards into the air with initial velocity v0, or actually, as it's also called, v0. After t seconds, we have that the height is negative 16t squared plus v0 times t. All right, so we see what happens here is we have this negative 16 here, which is roughly half of the acceleration due to Earth's gravity. And over time, this term with a negative 16t squared is going to become larger than this term with the v0 times t, which means that its velocity would start going the other direction, i.e., the object starts falling down. So the object starts at rest and then it's shot upwards at t equals 0 with an initial velocity of v0. So right here is the instant at which the object starts moving. And then you have the object traveling straight upwards. Those green arrows there represent the force of gravity acting on the object, which is slowing it down until eventually the object stops mid-air for an instant and begins to go back down. This is a very, very common sense kind of occurrence. All right, we have an arrow being shot from the ground into the air at an initial speed of 108 feet per second. And we want to know when the arrow will be 180 feet from the ground. So we have the arrow, it starts going up, turns around, and then goes downwards. So supposing that the arrow actually does make it up 180 feet from the ground, well, it's going to pass that height twice, once on the way up and then again on the way down. So that's something that we want to keep in mind. All right, according to the height of the arrow is equal to negative 16 t squared plus the initial speed is 108 feet per second going upwards, assumedly, so 108 times t. We want to know when it's 180 feet from the ground. Fine, so we'll replace that h with an 180, and then what we're going to do is solve for t. Let's get all the stuff on one side. All right, so then I just have to solve it. Let's use the quadratic formula. So t is going to be equal to negative b. Since b is negative to start with, it's just going to be positive 108 plus or minus the square root of b squared would be 108 squared minus 4 times a is 16 times 180 all over 2 times 16. So we get that t is equal to 108 plus or minus 12 all over 32. So what we want to do is round the time in seconds to the nearest tenth. This will be about 3.8 seconds. And the next guy has an exact answer of 3. So as far as our summary statement is concerned, we can just say, okay, the arrow gets shot upwards, it hits a height of 180 feet at around 3 seconds the first time, and then again on the way down after about 3.8 seconds. Anyway, that about wraps it up for section 9.5 about applications. Next up, we're going to talk about graphing quadratic functions, a couple different ways.